Hi Deepak, can you see? Can you hear me?
Yes, sir.
And can you see the screen?
Yes, sir.
Okay. Let us start today anyway. Let us join. Okay. Could you watch this week's lectures on caps and inductors?
Yes.
Okay. Do you have any doubt on this week's lectures or maybe previous week's lectures or questions or anything? Any question? All right. We'll start then. This week is mostly about capacitors. Very few questions on inductors. Um, so inductor and capacitors are the two mm, such components of electrical engineering, electrical circuit where there is ideally no loss. There is one more component that has ideally no loss is a switch. So mm, capacitors, inductors, and switch. These three components are ideally lossless components in electrical engineering, and later on you will see that there are several networks, electrical circuits which are made with only these three components, and those circuits are called power electronic converters. They are used to convert the form of energy, means it's only electrical, but the way it is available to you to the way you need. So for example, you have DC and you need AC, or maybe the other way around. That is why we need these things. Anyway, that is not a topic of this course. Okay. Mm, right. So we'll start with the problems then directly. I don't know why in this course this year, I mean, I'm taking the course of the first time this year, but this is the first time in an NPTEL course I am not getting any doubt at all from the students. Whether you are guys are able to understand everything in the lecture, I don't know. If that is the case, then it's very fine. Okay. So there is a circuit given here that consists of capacitors only, and the capacitance measured between terminals R and Y we have to find. So between this terminal, this point and this point, we have to find the capacitance. So you can see that it's a bit complicated to directly understand the circuit. So in such case, what we will do is we'll redraw the circuit and see whether we can simplify the circuit. Okay. See point B, if you see here point B, it is grounded through this wire, short circuited. So if I draw R here, say R point is here, and say this is B, which is grounded, then we can see that the capacitor CC that is connected to B, and also the capacitor CS is connected to B, and there is another capacitor CC that goes to Y. Okay, we'll look into it later. Now if you look at other point Y, what we have is another capacitor CC goes to B from Y, so CC, and another capacitor CS goes here, and there is a capacitance between R and Y, which is CC again. So the circuit basically looks like this. We did not draw the ground anymore, it doesn't matter. Right now we have to find the capacitance between them. Now we can directly write from here. So if I write R again here, then this capacitor is CC plus CS, and again we have Cc, again Cc plus Cs, and they're shorted. This is why we have to find between them. So as you can see that these two capacitance Cc plus Cs, they are in series. So what will happen is, so between R and Y there is one capacitor here which is Cc, and another one which is Cc plus Cs by 2. They're in series. Now these two are again in parallel. So between R and Y there is a capacitor whose value is Cc plus Cc plus Cs by 2. So now whatever values they have given, Cc10, Cs6. So 10 plus 10 plus 6 by 2, it gives you 18. 18 farad. 18 farad is a extremely large value of capacitor. Anyway, the capacitors that we'll get to buy from the market are microfarad or at most millifarad. Mostly nano and picofarads are also available for electronic circuits. 18 farad capacitor will be very large in size. Okay, any doubt here in redrawing the circuits? See, if you look at figure 1 here, it's kind of difficult to make out that this capacitor Cs and this capacitor Cc, they are in parallel. Kind of difficult to make out. So we redrew the circuit like this, and we got this. Any doubt? Tell me, or then I will go to the next question. Okay, then I will assume no doubt since there is no response from your side. We'll go to this question. The question says a voltage waveform Vt. The voltage waveform is a function of time. 15t squared plus 2t is applied across a 2 Henry inductor for t greater than 0, greater or equals 0, with initial current through it being 0. The current through the inductor at t. Okay, so you have to find out the expression for the current through the inductor. Again, 2 Henry is a very large inductor. Okay, if you really try to make 2 Henry inductor, it will be very, very large in size. Practical values of inductor lie in the range of micro to milli Henry, very large inductors, and nowadays we are trying to make it even more small. Inductor takes space, a lot of space. Okay, so V is given. Now we have seen this equation, this thing we discussed during our very first class, that uh, if you have, and Deepak, please turn off your camera. Yeah, if you have an inductor L like this, and if you take the voltage across the inductor in this direction and the current across the inductor in this direction, then you can write V equals L di dt, right? Here the directions are very important. Polarity of voltage and current direction, this is very important. Okay, this is the most general equation for an inductor. Doesn't matter what kind of voltage you are giving or something, this will hold everywhere. Now that we have here, so what we can write is 15t square plus 2t, that is equal to L di dt. We have been asked to find out the current expression. So what we will write is L di equals 15t square plus 2t dt. Now we have to integrate. Now, although these things should be known to you by now already, but still I will just tell once again. You have been asked to find out an expression for the current through the inductor. So basically you have to find out I as a function of time, like this. So this is a kind of general equation that you're trying to find out for current. And it starts from t equals 0. So 0 to the limit will be t. T means any t. Okay. So that you can put the value of t and you get the current flowing through it. And at t equals 0, the current was 0. It is mentioned in the question with initial current through it being 0. So 0 to, again we are trying to find the general current expression, so 0 to I. Okay, whenever you are putting limits in integration, be very careful. Now, so what we get is Li equals, we have to integrate this, so this is t cube by 3, so 5t cube plus t square by 2, so t square 0 to t. I should actually write here 0 to I. So what we get is Li equals 5 t cube plus t square. Now L is 2, they have given 2 Henry. So the current will be right hand side divided by 2. So 2.5 t cube plus half t square. Any doubt? Quite a straightforward question. Deepak, I can see you are unmuting yourself, but I can't hear anything from you. Are you saying something? Okay. So if there is no doubt in this question, yeah, Deepak. Okay, we will go to the next question then. If there is something, you can write, Deepak, in the chat. Okay. So the next question, the switch. So there is a circuit, RL circuit. Initially the switch was open, so definitely no current in the circuit. And the question says the switch is closed at t equals 0 in the RL circuit as shown in figure. The initial current through inductor is 0. Has to be 0, no other option. Now determine d2 dt2. Right? Now, so basically you have to find out the equation of current through the RL circuit. We know, do you want me to derive this? The equation of current is this. Tell me, do you want me to derive this? Or you already know? You should already know actually. Just write V equals L di dt plus IR. Now what you have is V dt equals L di plus can you solve like this? IR dt this voltage is constant V dt. Then what we have to do, we have a current here I. So V minus IR times dt equals L di. So dt equals L di by V minus IR. Now if you integrate, you will get t equals L log of V minus IR. There will be one R because it is an R with this. Now if we do this, you will get minus t by L by R. So take this side and take log. It is equal to V by V equals IR. Right? Now by rearranging, you will get this. Now there is one way I will tell you, by which you can not remember, but you can instantly write this. Now the expression that you are trying to find out, it is either like this or like this. Okay, like this. Now if you have the top one, this one kind of expression where at t equals 0 the value is 0, so you will have 1 minus e to the power minus t by tau kind of this kind of response. On the other hand, this will be simply to the power minus t by tau kind of response. Say for example, current through an RC circuit, it will be like this. Okay, so once we have that, but anyway, since we have to find out d2i dt2, I think we do not need to start from this. We can directly start from v equals IR plus, no, let us start from here. We have two variables. Don't worry, we'll start from here only and see if we can, although we'll get the same thing. So di dt will be v by r, that goes to 0. So it is basically ddt of minus v by r to the power minus t by tau. So it comes, this minus minus cancels out, 1 by tau comes out, 1 by tau times v by r e to the power minus t by tau. Tell me if I am making a mistake anywhere. Now once again, if you derive, again you will get 1 by tau coming out, so this will be 1 by tau squared v by r e to the power minus t by tau. Everything is given here. Tau, as I said, is L by r. Can you do this and tell me what is the final value? Just find out minus r squared. I couldn't hear you, Renessa. Okay, they have said that t equals 0, t tends to 0. So e to the power 0 is 1. So basically just find out this. Just find out minus rv by L squared. So what is rv by L squared? R is 5 into V is 50.
Minus 0.
Should be 0.75 minus. So you see one thing here, it is d2 dt2. Okay, so rate of rate. So the thing is, just take what is the takeout of this takeaway of this question. If you look at the current, it's not like this. If you look at the current, it becomes constant after some certain time, so it increases and then becomes constant. Mathematically it is never constant, mathematically it is always increasing, but that obviously never means not always increasing, I'm sorry. It never reaches the steady state value. The steady state value is v by r. Mathematically it never reaches this value, but you will practically get to see that it has reached v by r. Now this much of current. Now the thing is, definitely di dt is always 0. Sorry, di dt is always positive. But the rate of increase that reduces means the current is increasing, but more the time goes, it is increasing slower, right? That is why you are getting this kind of convex curve.
Right?
I'm sorry, your voice is breaking. Go again.
We can do it by using KVL also. Like starting, like doing an equation with KVL.
Yes, we did it by KVL only. That is the only tool we have to solve this circuit. By KVL only we did. This equation I wrote, you can do it in this way also. Say if you write V equals IR plus L di dt. Now
So
if
my
you
equation is I of t is equal to minus 10 di a function of t by dt.
if you write like this, so this plus L d2y dt2. Now definitely this is 0 because it's a constant voltage, and di dt you can replace from this equation to here. So di dt is V minus IR by L. So it becomes R times V minus IR by L plus L d2I dt2 equals 0. From here also you can directly find out what is asked in the question. Okay, any doubt in the question? Easy question. We'll go to the next. All right. So there is a circuit here. There is a switch, and the switch is thrown from position A to position B at time t equals 0. The energy taken from the 3-volt source to charge the capacitor is how much? Now, let us look at the situation before t equals 0, how the circuit would look like. The capacitor is shorted, as you can see. This is a ground and this is a ground. So basically the capacitor was shorted. And whenever you are given questions like this, that it was the switch was here before t equals 0, it means that the circuit was at steady state before t equals 0. The circuit was a steady state before t equals 0. So if the capacitor is short circuited and steady state, definitely the capacitor was holding no voltage, no energy in it. Now at t equals 0, it is closed, or the switch is thrown in this way. Achha, anyway, we'll do this problem. Can you tell me what kind of switch is this? I will redraw the switch here. What kind of switch is this? What is this called? So this one can be connected at point A or maybe at point B also. And it is always connected at point C. So point C is either connected to point A or point B. What kind of switch is this? What is this called? Do you know? This kind of switch is called um, single pole double throw, right? Why single pole? Because you see here only one path is there. Say a current is coming through, sorry, say a current is coming through C. So it has to go either through point A or through point B, depending on the position of the switch. That is why it is single pole. And double throw, because the switch can be either at position A or at position B. So this is called a single pole double through switch. The regular switch that is present in your plug point to turn on your lights and fans in your room, they are like this. Okay, this single pole double throw is called SPDT in short. Okay. Now this one, you see, this is also single pole. Only one current can flow through it, one path, but it is single throw. Now you may say that I can turn it on or turn it off. It is double throw, but turning off is a meaningless throw. Okay, that is interrupting. So it's single pole and single throw. So this is called SPST. Do you know in your home possibly where there can be a SPDT switch, single pole double throw switch? If you have a staircase lighting, say a light in the middle of the staircase, which you can turn on and off both from the ground floor and from the first floor, say, those switches are single pole double throw switch. I will show you the circuit after we solve this problem. Very interesting. So anyway, we'll look at the switches now. So this is a single pole single throw
We can
switch.
start by doing applying KCL at B, right?
I'm sorry. Sorry,
We
go
can
ahead.
start it. We can start it by. I have actually come to the answer. So it is coming 0.9.
Okay, we are not solving this question as of now. We are discussing about switches. We will look into the question after we are done discussing about the switches. Anyway, SPDT and SPST we saw. Now there are double pole switches also. Say for example, it's a simple. Say you may have this kind of MCB at your home. So one of them is connected to the neutral phase, say, other one is connected to the neutral, and it's like this. Generally, we draw these switches in this fashion. Sorry, we draw two lines like this, which means these two switches are mechanically connected. You cannot close one and you cannot keep the other open. If you close, both are closed, both are thrown together. We sometimes draw them like this, and it's like this. So what kind of switch is the? Can you tell me? Looking at the previous examples. See, how many poles does it have? You tell me. How many poles does it have?
It has two poles.
So it has two poles. Two currents can flow in this direction, but it has a single throw. Only you can turn it on or off. So it's a double pole single throw switch. You can have also say switches like this. Draw it other color like this. So the okay, I will draw this with blue. So the switch that comes, the blue one, it can either be connected to red or it may be connected to the connected to green like this. So it is also double pole because two paths of currents are there, but it has two meaningful throws. Right? It can either let the currents go through the red wires or through the green wires. So it's a double pole, double throw switch. Similarly, you can have triple pole single throw switches. Triple pole single throw switches are there in three-phase MCBs. Three-phase circuit you will study in this course only. Maybe the 9th lecture is on three-phase circuit or some 9th or 10th. Three-phase means three live wires come and they will be like this. It will be a triple pole single throw switch. There can be triple pole double throw switches also. Number of throw may be more than two also, if you have any kind of requirement. Anyway, so these are different kind of switches that you will encounter. Now we'll look into the question. The question says it was at steady state and we have been asked to find out the energy taken from 3-volt source. Now see, there are So the capacitor has some energy is C, which is half CV squared. And since there is no current in the circuit at steady state, the capacitor voltage must be equal to the supply voltage KVL. There is no current in the circuit. So half CV square, you can find out what capacitor is 0.1 microfarad. So half into 0.1 into 10 to the power minus 6 times 3 squared, some value we will get. This much energy is stored in the capacitor. Okay, we'll remove this discussion below. Switch discussion so that we have space here. Just a second. Now, capacitor has some stored energy, and definitely it has come from the battery because there is no other source of energy. But while the energy was going to the capacitor, there was some current also in the circuit, and the current was flowing through the resistor, right? Current was flowing through the resistor. So there was some loss in the resistor, and the question is how much energy is taken from the voltage source. So you have to find out the loss. Now, so what is the current expression through the circuit? Current is V by R e to the power minus T by tau. How do I know it's like this? Because I know that the current is decaying current. So the initial current was non-zero. So if you put T equals 0 here, you will get I equals V by R. And if you put T equals infinity here, you will get I equals 0. E to the power minus infinity is 0. So this type of current is flowing through the resistance, right? So now if I can find out the power, the energy, we can find out how much is lost. So I squared R is the power, right? I squared R is the power lost in the resistance. So it is V by R squared to the power minus 2T by tau. This much power is lost. Now we have to find out the energy. So energy in resistance, let us say ER. Let me write it as small p because it is instantaneous power. Can you appreciate that this power expression that I have written here is instantaneous power? Because you see it is a function of time. That's why I am writing it with a lowercase p. Now energy is integration of power p dt integration. Now you tell me the time. It should be 0 to how much? Zero to how much? What is the span of the time? What should be the integration limits? It should be 0 to infinity. Because if you look at this current becomes 0. Mathematically, it becomes 0 only when t tends to infinity. So the energy that we are calculating, we have to integrate the power from 0 to infinity. Right? Now let us integrate. So we have v squared by r squared comes out of the integration, and e to the power minus 2t by tau dt 0 to actually should not write infinity like this. Let's say t tends to infinity. Now it becomes minus. What happens in integration? The opposite things comes out, right? So minus tau by 2 times v squared by r squared e to the power minus 2t by tau 0 to t tends to infinity. Now what we have is minus tau by 2 v squared by r squared times, we should write like this, limit t tends to infinity e to the power minus 2t by tau.
So we also start this by applying KCL, right?
Sorry,
We could have also done this by applying KCL.
why do we apply KCL? It's KVL only.
No, sir, I have applied KCL, sir.
Okay, that's fine if you can do it by KC, not a problem. Now, at t tends to infinity, e to the power minus infinity is 0, right? E to the power, if you draw e to the power t versus t, the curve looks like this. At 0, it passes through 1. At minus infinity, it is 0. Minus infinity, it is 0. At plus infinity, it is infinity. So e to the power minus infinity is 0. So what we, this one is 0. This is minus 1 we have. So this minus 1 neutralizes this minus. What we have is, I'm sorry, I changed that. What we have is t by tau times v squared by r squared. Now what is tau? Tau is RC. RC network. So time constant is RC by 2 times v squared by r squared. So what you get here is half CV squared. So this is a very interesting observation, that energy lost in the resistor also is half CV squared. So the voltage is V, capacitor is C. At steady state, there is half CV squared energy stored in the capacitor, and during the process of energy transfer from the voltage source to the capacitor, there was a power loss, and the total energy lost in the resistor was also half CV squared. So the total energy that you have is half CV squared times 2, it is CV squared. So it is 0.1 times 10 to the power minus 6 times 3 squares. 0.9 millijoule is the answer. Okay, you remember this observation. I find this quite interesting, that the energy stored in the capacitor is half CV squared, whereas the energy lost in the resistor is also half CV squared. This kind of calculations are important, because later on, if you maybe you will study other things where you have to design the circuit. Now suppose you calculate that you need a 1 ohm resistance at some point of the circuit. You have to also find out how much is the power loss in the circuit. Okay, say maybe it's 1 ohm and you find out that the power loss is 0.5 watt. Then you go to the shop and you have to ask for a 1 ohm half watt resistor. Available powers are quarter watt, half watt, 1 watt, 2 watt, and I think and higher also are there. These are carbon resistance I'm talking about. So if you go to a shop and simply ask for a 1 ohm resistor, the shopkeeper will ask you. He will first make fun of you, then he will ask you what is the power rating that you need. Otherwise, he cannot give you, right, how much power dissipation you need in the resistor. Similarly, if you go to buy a capacitor, simply telling him that I need maybe 470 microfarad capacitor won't do. You have to also tell him 470 microfarad 100 volt. Then only the shopkeeper can give you a capacitor. Okay, so when you are designing the circuits, you have to also find out how much power loss is there in the resistance, and in that way only you have to buy or make your BOM, bill of materials, for the circuit that you are going to make. Okay, so I said that we will discuss a little bit about this one, single pole double throw switch. So I think you know about those lighting systems, right, where you have two switches for one light. Maybe the light is somewhere in your staircase and you can turn it on and off from both ground floor and first floor. And you will be amazed to see that sometime you so-called turn off a switch and the light turns on. Somehow you so-called turn on the switch and the light turns off. This thing happens, right? We'll look into the circuit how that is made.
Sir, kindly listen to my equation once.
Okay,
So, sir, if you're applying KCL at point B, then I1 plus I2 is equal to 0. Then will be V
where are you
as.
getting I1 plus I2? Where are two currents here?
No, I have marked it in the diagram.
No, Where from is our two currents coming here. It's one simple RC
From B,
circuit.
no, from B it is going. Current is going, so it has been marked I1, and down it is going, so it has been marked I2.
So I1 is equal to I2.
No, I1 plus I2 is equal to 0 because the directions are different.
So I1 is equal to minus 2. Are you making this one as I1 and this one as I2 like this? Are you writing?
Yes, sir. The directions are just opposite, sir. I1, whatever direction I've marked,
So
I have
why are
marked
you
it
why are
opposite.
you why are you making your life so difficult? Why can't you simply take a current like this? See, once again, I am saying do not concentrate on what theorem or what law you are going to use. Concentrate on the circuit. This is a simple equation, right? We all already know this. Plus 2 level physics. This is I, and from here we know I squared R. Then I integrated the power to get the energy. Your final answer is matching?
Yes, sir. It is matching.
Okay. All right. So we'll look into the circuit, that how is it possible to control a light, say any load, it can be any load, let us say light from two positions at a time. Now say this is the live wire that is coming. Okay. And this is the lamp or any load. I am drawing lamp. So this is the lamp that you are trying to turn on and turn off from certain position. Now what happens is this live wire comes and there is a switch, a single pole double through switch here, sorry, like this, and there is another single pole double through switch here, like this, and the connection goes like this. Okay, let me draw. Yeah, and the connection goes like this. The live wire goes to the middle pole of one switch. Then these poles are connected like this. They are connected like this. And this one goes to the lamp. This one goes to the lamp, and the other end of the lamp that goes to the neutral directly. Okay. Now, say if I call this switch S1 and if I call this switch S2, maybe S1 is present at the ground floor and S2 is present, say, at the first floor. Now these switches actually look similar to any other switch on the switchboard, but actually if you open the switchboard and find the switches at the back of the switch, you will see that while other switches have, very often we call these things as pillar. I cannot draw a line. Anyway, pillar, while other switches have two pillars like this, there is 2 points where you can connect wire. The staircase switch will have three pillars like this, three ways where you can connect. So this one is the middle one here, and these two are the other. So the live wire comes maybe from the ground floor, it connects here, and these two wires from the ground floor switch, they go to the first floor. So these two wires, they have to travel all the way to the first floor. And first floor switch, again there is a DPDT, sorry, SPDT, like this. It has 3 terminals, and this terminal then goes to the light, and then the other end of the light, it goes to the neutral. Okay, now look at the operation. Say I will mark the points. Say I mark the points as say 1, 2, 3 and 4. If I mark, now you see, if switch 1 is at position 1 and say switch 2 is at position 3, say S1 and S2, if I write like this. Now if switch 1 is at position 1, switch 2 at position 3, what is the state? Position 3. So tell me whether the light is on or off. Can you understand the circuit? Yes, no. If you cannot understand, tell me no. Don't keep quiet. Tell me no. Write in the chat box no. Yes. Am I audible? At least here you say yes or no. Oh, if I'm not audible, how do you say no? Someone is typing. Deepak. See, it's very frustrating when you don't talk. I know you guys are there. I don't know whether you guys are there or not. Could not understand. Okay. SPDT, could you understand that this switch I can throw at 1 or 2 and the other switch I can throw at 3 or 4? God knows. So if it is connected at 1 and the S2 is connected to 3, there is a flow of current. The flow of current is like this. Goes to the bulb and comes back. So there is a flow of current and the bulb glows. Now you want to turn off the switch, turn off the light. You see, you can turn off the light from any place. You can turn it off from ground floor. You can turn it off from first floor. Just change the position of one switch. Just say, let us say I make S1 at 2 and S2 at 3. So how does the circuit look now? The circuit now looks like this. It is connected at 3. It is at 2. So there is no way that the current can flow. So it is definitely off. Now again, from any position you can turn it on. Say from S2 you can turn it on. Simply change the position of the switch. So it is 2 and 4. Again the light is on. So you have independent control. You can turn on the light and turn off the light from any place. Okay. Engineering is not about solving given circuits at all. It's about making circuits. So try to understand these things also. And try to be an engineer, not a problem solver. All right, we'll look into this question. A square pulse of 4 volts amplitude is applied to a CR circuit. CR circuit, I don't know where from they got this term. Shown in figure. The capacitor is initially uncharged. Very good. The output voltage at T equals 2. So the output voltage is basically the current flowing through the resistance, basically the voltage across the resistance, right? Now we know the equation of the current. The equation of the current is V by R e to the power because here is the current, same R. So just IR V to the power minus T by tau. Now you put what is the question is 4 volt e to the power minus 2 second and tau is RC. R is 1K times C. Where is C? C there is 0.1 microfarad. Someone dual tell me the value, how much voltage is there, then we will show some more, show something else. Someone answered the okay. Zero, I am also getting zero. How is it coming zero? It can never be zero, right? I think these ones are not correct. It can never be negative for sure. It can never be 4 volt. And given the time and the time constant is quite small. What is the time constant? It's 0.1 micro times R is 1K. Time constant is 0.1 millisecond. So there are 10,000, 20,000 cycles covered by this. So it can never be 4 volt also, 3 volt also, it has to be 0. Answer is wrong, it cannot be. The solution says that at steady state, this is open circuit. So this is 4 volt. That cannot be. That cannot be because there is no current through this resistance. If there is no current through this resistance, how can there be a voltage? Okay. Has to be 0 volt. Equation is correct. You just look at it and just think, even without doing the problem, if you think, see, this cannot be the case. Negative cannot happen, right? 4 volt cannot happen because it's reducing. Maybe they're doing some mistake. It cannot be, because you see now what is happening. The voltage, as soon as you apply the voltage, there is no current through the capacitor. And sorry, there is high current through the capacitor suddenly, and it reduces like this. Now if this is the circuit current, if this is the circuit current, then the voltage across the resistance will also look like this, right? Now the question is, how much will be the value? Now if you look at RC comes out to be 0.1 millisecond. 0.1 millisecond. Now in 2 seconds, how many time periods are going by? In 1 second there is 10, not 10, 10,000. So in 2 seconds there is 20,000. So there are 20,000 cycles going by. So definitely the voltage will be zero, because at state it is definitely attending steady state. So at steady state the circuit is like this. The circuit is like this. In a circuit like this, the voltage here can never be 4 volt or 3 volt. It has to be zero. No current through the resistance at all. No way this can be 4 volt. Now there is something, would not step the pulse. 4 volt comes, then at 2 seconds it is suddenly made zero, right? It's not a constant 4 volt. Had this been a constant 4 volt, then definitely this is zero. Now it is suddenly made zero. Then does that make any difference? We will see. This is going to be a little bit complicated. So if you have any doubt, make sure that you ask me. Now this circuit, before 2 seconds, for sure it goes to steady state, because it has only 0.1 millisecond of time constant. So at steady state, what happens if this is 4 volt, this is also 4 volt. Now they are saying that at 2 seconds the voltage is suddenly zero. Now if I consider that, then say this is at t equals to minus second. Now 2 seconds you suddenly make the voltage zero. Voltage zero means short circuit. Voltage zero means short circuit. Now if you see the capacitor was 4 volt, suddenly if you short circuit this, then the voltage that you are getting here is like this, 4 volt. So it should be minus 4 volt. Tell me, any doubt, or could you answer, or should I say once again? Should I say once again? The answer is minus 4 volt, because the voltage is made zero once again at t equals 2 second. Had this been kept kept constant 4 volt like this, it would have been zero for sure. Since it is made again zero, basically we are short circuiting. So instantly the capacitor voltage appears across the resistance. Then it reduces. Tell me, is it clear? I initially did not consider this fall of the voltage. Okay. Now we will quickly look into this. We will look at this circuit once again. It's a very interesting circuit. You will go through it maybe. Say a circuit like this. Okay. Now what you have is some input voltage Vi, some output voltage V naught. Now we just solved the problem. What we saw, that there was a pulse of 4 volt, 0 or no, 4 volt pulse is there, and we got this equation V equals c to the power minus t by tau. At t equals 0, V is V. So if this is V in, this is V out. Try to understand. At t equals 0, V output is equal to V input, and then it drops exponentially. So it was 0 initially. Suddenly it becomes 4 volt, and it drops like this. Again, after some time, you make it 0. So let us say it dropped like this and reached 0, stayed at 0, and it becomes minus 4 volt as we derived. So it likes like this. So if you keep giving the circuit pulse like this, you will keep getting response like this. Sorry, draw it properly. Keep getting response like this. So you see what is happening here. What you gave, this will be more clear to you once you study Fourier series and all in your higher classes. But say this square wave, if you look at the flat portion of the square wave, this area, this represents low frequency component of the wave. Whereas this transition, very sharp transition, always keep this in mind. If there is a sharp or sudden transition, that means it has a high frequency component in it, for sure. Now, this one at the low frequency component, the flat component, you see the circuit output is reducing. If you can if you can design the circuit properly, you can even get response like this. Response like this maybe will get if you can design properly, means very small. So you are giving flat top square wave like this, although the output that you are getting is like this only some sharp spikes you are getting. So sharp spikes means what I said is high frequency. So this circuit, what it does is, although you give it many frequencies, it only gives you out high frequencies. Output you get only high frequencies. Do you know what this circuit is called? That will give you only high frequency irrespective of the input. It blocks the input low frequencies and only let the high frequencies go through it. This is called a high pass filter. This is called a high pass filter. So this circuit is a filter. You can think this way: the capacitor blocks.
How that graph is made, I didn't understand.
Okay. So let us say we have derived the we have designed the circuit such that the time constant is very small. That means the transient dies down very fast. then what you will get is sharp spikes. Spike here, spike here, spike here, and dies down. Sorry.
What will be the values for the same?
Values of what?
The graph, uh, how the values are not, how it is means.
The peak will be something like this. Anyway, I cannot draw like this. So only high frequencies come out of it. This is called a high pass filter. So you know, right? Capacitor blocks low frequency but allows high frequency. That's why it's like this. There are high pass filters like this also. Say, suppose hypothetically you make a circuit like this. This is also a high pass filter. Why? Because the inductor will short circuit all the low frequencies and only the high frequency will go through it. Although this is not made. An even better high pass filter may be like this. Say for example, transmission line. No, transmission line is often modeled as like this. The equivalent circuit of a transmission line. The transmission line is basically a low pass filter. Anyway, these things you will get to learn in your higher class. Just showed you how filters are made. In this way only, there is a filter circuit. Sometimes we need to know only the pulses, only the change. There we have this frequency high pass filter. In digital circuits, sometimes we have to find the clock.
What,
From the clock
which
we
were
derive
mentioned
this.
number of times.
Sorry?
What is this term pulse which you are mentioning quite number of?
Pulse is this one, the green square wave that I have drawn here. This is a pulse. The square wave is not a pulse, this is a pulse. One time you get like this. There are several kind of signals. This is called a pulse. So if you have like this, it was 0, suddenly it becomes high and stays. This is called a step. If it is like this, it was 0, then suddenly starts increasing linearly. It is called a ramp. If you have like this is called a sawtooth. If you have like this is called a square wave. Okay. Anyway, you need not understand it fully right now. Just keep it in mind, maybe in your notes also, maybe some year later you can go through it once again. Once you study Laplace transformation and all, then analysis of this circuit becomes even more easier. All right. We'll look into this. Assume that the circuit in figure 7 has reached steady state before time equals 0, when the 5 ohm resistor suddenly burns out, resulting in an open circuit. The current at current IT, okay, that current through the 2.5 ampere circuit at t equals 0 plus means just after the resistor burns out. Okay, So what we have to do is we have to first draw the circuit at steady state, how it would look at steady state, and find out the capacitor volt. So at steady state, what happens? Capacitors, it's a DC network, that's why you can take the capacitors at open circuit. Means they are not carrying any current, but there is definitely some voltage across them. So 2.5 ohm, 2.5 ohm, and another capacitor here, open circuit, 5 ohm, this way. Now this is 1.5 ohm and it's 18 volt. Now definitely at steady state there was no current through this 2.5 ohm resistor. At steady state IT was 0, means before t equals 0. I should write like this. No, not like this, because we don't know when the circuit was turned on. So we can find out the current very quickly. So ampere current flows here also. Now if there is 2 ampere current flowing from this 2.5 ohm resistance, there is no current. So whatever voltage we have, say at point A, that is the voltage at point B also. In this polarity, this was holding 5 volt and the other one was holding 10 volt in this polarity, and there was a drop of 3 volt. Sorry, drop of 3 volt here. So 5 plus 10 plus 3, 18 volt. KVL matches. Okay. Now it was in this situation when what happens, suddenly the 5 ohm resistance is open circuited. You have been asked to find out the current just after the open circuit. That means you can assume that just after the open circuit, the capacitor voltage has not changed, right? That is what happens, right? We know that the current through the capacitive circuit is given by I equals V by R e to the power minus T by tau. So at T equals 0, current is V by R. That is, capacitor voltage has not yet started changing. That we can do 0 minus, 0 plus, just after closing the switch. So we can now solve the circuit. We have to draw it once again. What happens after the resistance burns out? I don't think we will need this anyway. Um, Capacitor here. Capacitor here, open circuit. And there is a voltage of 5 volt. And other things. Now you see, we need not bother about other things because in this loop, the current will be decided by the capacitor only. So right after this incident happens, a current starts flowing, and we can assume that t tends to 0 plus the capacitor voltage has not sufficiently changed, because capacitor voltage takes time to change. Now 5 volt and flowing through a 5 ohm resistance, 2.5 2.5 in series, so it has to be 1 ampere. IT is given on the other direction. You see the arrow is from left to right, so the answer will be minus 1 ampere. Any doubt here? No, sir. Okay. We'll go to the next question. Figure 8 shows waveform of the current passing through a resistance of 1 ohm. Energy absorbed. Now we have to find the power, right? We have to find the power, instantaneous power. Then we have to integrate the power to get the energy. Now life was easy when current was constant, but here the current is not constant. So we have to find out the current as a function of time here, right? So what we can say is from t equals 0 to 2 second, current is mx plus c. C is 0, m is 6 by 2, 3, 3t ampere, right? 3t ampere. And from 2 to 4, 6 ampere, right? Now let us find out energy for the first 4 seconds, so 0 to 4, p dt, 0 to 4, I square r dt. R is constant, I will take it out. Now 0 to 4 we can break, 0 to 2, I square dt plus 2 to 4, I square dt. So what we have is, now at 0 to 2 we know I is 3t. So 90 square dt plus, and 2 to 4 we know it's 6. So 36 dt. 0 to how much? Sorry, 2 to 4. Now if you do the integration, 90 square becomes 3t cube. 0 to 2 plus it becomes 36t from 2 to 4. So what you have is 24 minus 0 plus 4 minus 2. So it becomes 72 plus 24, 96. How much is R? R is 1 ohm. So 96 joule. Right? Just check whether I've done any calculation mistake. Ninety-six is correct. Okay. Let me give you one hint, not hint, a tip maybe. Sometimes this may be required in some. Say, I have done this problem like this. Say 0 to 4, then I have broken it between 0 to 2 and 2 to 4. Like this. Now suppose instead of the current being like this that they have given in this question, say the current they give you is like this. It increases in ramp. Say I told you this is a ramp. So the current is increasing in ramp. The current increases in ramp, then again it reduces in ramp, maybe it's a. And say you are asked to find out the total power or total energy absorbed by the resistance. in this whole time. There can be a question like this. Now what I'm going to tell you, see, look at the first segment of the current. If you have to find out the equation IT, it is very easy to find out, right? Simply like this 3t as we find it out here. But for the second part, you have to write IT as mt plus c. Then you have to extrapolate this and find out the m. Or maybe since you know this point and this point, from there you have to use that x minus x1 by y minus y1 and calculate the current like this equation. Then you can do the integration like this. But if you do it in this way, it becomes a little bit complicated. Complicated in the sense you have to do a lot of calculation. So in such case, what you do is, see, you have been asked to find out the energy. So you can find out the energy during this time. You can separately find out the energy during this time and simply add them up, right? They will not affect each other. Simply find out the energy. So you do the first part like this, and while solving the second part, you assume that the current is like this. At 0, it was here, and it is like this. So what happens is the calculation of your current and power becomes much easier, and that will save you a lot of time. Basically, what I'm talking about is origin shifting. The integration will also be easier because you will not have any constant term if you write the current like this. One less term in the integration, and then add up the energies. Okay. Do you get my point? What point I tried to make here? Okay. Now they are saying similar waveform of the current as before. So this much current like this passes through an inductance of 2 Henry instead of the resistance. Determine the amount of actually there is kind of amount of energy absorbed. Amount of energy is never absorbed by the inductor. Inductor does not absorb energy. What it does is it stores energy. Ideal inductor. Now if I draw the current, say the current was like this. Now the energy stored in an inductor is half Li squared. So if the current is linear, the energy has to be parabolic. Now from here, the current becomes constant. So the energy also becomes constant. So you see here, we are not talking about energy dissipation like before. It's about the energy stored in the inductor. So if at this time, this much is the current, then at this time, this much is the energy stored in the inductor. If this is the current, then this is the energy stored in the inductor. So at 4 second, the current was 6 ampere. So at 4 second, the energy stored in the inductor was half into 2 into 36 joule. This is not the amount of energy absorbed. This is at t equals 4 second, this much energy is stored in the inductor. Okay, not the energy absorbed. So this second plot here, E plot that I'm showing, shows at every instant how much energy is stored in Okay. How many more problems? 3 more problems. Half an hour left. Okay. So in the circuit shown in figure 10, the voltages VC2, VC3 under steady state conditions respectively are. So we have to find out how much voltage is stored in the capacitor at steady state. Let us redraw, but although I'm redrawing for you, but you guys have to make an habit that without redrawing, you should be able to write the voltages, means at least the currents in the resistances and capacitor voltage. Okay. At steady state, the capacitors are open circuit because it's a DC network. So at steady state, the circuit looks like this. I should write capital also here because it's a DC and we are talking about steady state. Maybe in your second year, or I don't know whether you guys are in that which year of your BTech, you will learn how to solve the transient of these circuits. There you cannot write capital V, you have to write small v. Okay. Now this is 10, this is 40, sorry, 25. So as you can see that during steady state, this loop does not carry any current. This 25 ohm, this carries no current. Current only flows in this 10 ohm and 40 ohm resistance. So 100 volt gets divided into 100. Sorry, this is VC1. VC1 is 80 volt. This capacitor is holding 80 volt. But the question is VC2 and VC3. Now, since there is no current through this loop, there is no current through this loop, so there is no voltage drop across the 25 ohm resistance also. So basically, this problem boils down to this simple problem that you have two capacitors in series. Their total voltage is 80 volt. Then what is, and their values are C2 and C3, then what is the voltage distribution? How much voltage is C2 holding? How much voltage is C3 holding? Now, I think you have already solved this kind of circuit in your +2 level, that before the circuit was energized, the capacitors were not holding any charge, right? 0 volt. Now, if you look into this portion of the circuit, this plate of capacitor C2 and the other plate of capacitor C3, they are isolated from the whole system. They are isolated, electrically isolated. So the total charge in this system is always 0. There will be charge distribution, but the total charge is 0. So if it is like this, if the capacitor C2 is holding a charge of Q, means plus Q here and minus Q here, C3 should also hold a charge of Q. This is charge conservation, law of charge conservation. So that in the red box, the isolated system has still 0 charge in it. Now we know the charge distribution. We know that, so we can write that VC2, capital V I will write, capital VC2 times Q. Q equals CV, sorry, VC2 equals Q equals C3. Case what we can say is Vc2 by Vc3 equals C3 by C2. So what is that called? Reverse proportion, or what is that called? Right. Inversely proportional. The voltage is distributed in inverse proportion of the capacitor values. Voltage is distributed in inverse proportion of the capacitor values. Now, if Vc2 and now if C3 by C2 is how much? If we can write C3 is 3 and C2 is 2, it's given in the question. 3 farad and 2 farad. So the capacitor with lower capacitance will hold more voltage. So basically now what you have to do is you have to divide 80 volt in 3:2 ratio. So 3 by 3 times 2 is 5, so 16. So it is 48 volt here and 32 volt here. Vc2 is 48, Vc3 is 32. Is it clear? I think you have already done these questions in your +2 level physics. Any doubt? Okay. We'll look into this question. The circuit in figure 11 has reached the steady state with the switch closed for a long time. And then the switch is opened at t equals 0. Find the voltage. Oh, the same question as that one, when the resistance burnt out. We will not redraw this circuit. Okay, in this way only we'll do. And it is easy also. So it was closed for a long time. This one was volts. So 1.5 ampere current was causing a drop of 4.5 volt, 6 volt, 4.5 volt. You add them up, it is 15. So this was the current at steady state. Now look at the voltage. Now clearly this capacitor was 4.5 volt. What about this? In this loop, it is 15 volt, of which 4.5 goes away here. So it has to be 10.5 volt. This capacitor was holding 10.5 volt. Right? You can do it from here also. 6 volt plus 4.5 volt adds up to 10.5 volt. First, you tell me, is it clear how I found out the capacitor voltages? Okay. Now the question is, switch is open at the voltage Vs at t equals 0. Right. So voltage Vs means now the switch is opened. As soon as you open a switch, there is a voltage across it. When you close a switch, when a switch is closed, it is carrying some current and the voltage across it is 0. When you open the switch, it is blocking some voltage and current is 0. Now, the question is the switch is opened instantly, then how much is the voltage across it? What we can do is we can simply draw this part of the circuit. That will be enough. This is the switch opened now. Instantaneous element, it respond instantaneously. Now if this is 4.5 volt, now definitely once you open the switch, again the voltage distribution, charge distribution in the capacitor changes and the whole circuit goes towards the new steady state. But that takes time. Instantly after you turn on or open the switch, the capacitor cannot instantly discharge. So whatever voltage you had in the capacitor, you can say for t equals 0 plus, it will remain there. So for t tends to 0 plus only, we can write this equation. There's this voltage Vs, it's a drop, say minus Vs, and it's a rise plus 4.5 equals 0. So what we have is, right after the switch is opened, the voltage across it is 4.5 volt. Okay, same question as that one. Any doubt? All right, we will go to the next question then. Last question for today. In the network, okay, someone replied, said there will not be any drop across the 3 ohm resistance. No, how can there be? We turned on the switch, no? We turned on the switch. If you turn on the switch, there is given by V equals IR. So if the current is 0, voltage is also 0. That was a confusion because I wrote I not equals 0. Okay. Open circuit. The current cannot flow at all. I want you to carry these ideas from this course. That is, a switch, when it is closed, it is carrying a current. Say, for example, the switch at your room, you think about it. Say the fan switch. As soon as you turn the fan on means you close the switch. It is carrying some current, maybe say some 20, 50, 30 or 100 milliampere current it is carrying, let us say. And what is the voltage across the switch? 0. Ideally. Now you turn off the switch, the current stops. But look at the circuit when you turn off the switch. So this is your AC supply. Now definitely the voltage across the load is 0. But the source has some voltage, V source. So the switch is now blocking the source voltage. The switch is now blocking the source voltage. So the switch must have the capability of blocking the source voltage. That's why if you see, when we buy domestic switches, we do not mention the voltage. We just go to the shop and say that give me a 5 ampere or 15 ampere. switch. But if you look at the packet of the switch, it's also written 230 volt. That means it is RMS, 230 volt RMS. That means the maximum voltage the switch can withstand is 230 root 2 volt. Obviously, it's not designed at this limit exactly. There is some space, means margin, but that is the voltage rating of the switch. If you connect this switch to say a 600 volt supply, I am not turning on the switch at all. Forget about the current. Forget about the current. I am not turning on the switch at all. Switch is off, but it is connected at 600 volt supply. This switch will fail. Fail means it will go through dielectric breakdown. This 600 volt, because it is not designed to withstand 600 volt. 600 volt will cause dielectric breakdown through the switch and current will start flowing. This is why a switch is rated for both current and voltage. Later on, when we will study power electronics, you will see that we use transistors as switches. Different kind of transistors as switches. All of them have a certain voltage rating and a certain current rating. Both of them matters. If it carries more current than rated, it will burn due to heavy temperature, heavy heat generation, which it cannot dissipate. And if the voltage is more, it will not burn. It will, you can say, burst because of dielectric breakdown. The insulation will fail. Okay, these ideas you keep. You are going to be engineers, so these things you should know apart from solving problems. Okay. We'll look into this question, last one. In the network shown in figure 12, the circuit was in steady state condition with switches closed. This one is finally a circuit with inductor. At the instant when the switch is opened, the rate of change of current. Okay. Now, capacitor circuit, DC circuit with say a DC circuit, there are capacitor inductors. At steady state, capacitors are open circuited and they are holding some voltage. And current. Right. So at steady state, what happens? 4 volt. So 2 ampere, 2 ampere. Current flows. So the inductor is carrying a current of 2 ampere. So basically what is happening about the power of the inductor? The inductor is simply storing a power of 4 joule. Simply it has this much power stored in it. It is not absorbing any more power. It is not giving out any more power. Simply it is holding this, sorry, not power, energy. It is simply holding this much of energy in its core. Like that. Okay. And there are energy being dissipated in the resistances. Now the switch is opened. What will be the rate of change of current? So if the switch is opened, we need not draw this side of the circuit. We can simply draw the circuit like this. Now this is L, say this is R, this is 4 ohm, okay? They come in series. You understand that, right? If I open the switch, only this loop is functional. So these 2 ohm resistances, they come in series. Let us write KVL. So I will take current flowing like this. So if the current flows like this, there is a voltage drop here like this. IR. Now if I write the KVL, if this is VL, say KVL, what does it say? VL increment minus IR reduction is 0. So L di dt is equal to IR. Now what we have is di dt is IR by L. So as you can understand that in this circuit, the current will keep dropping. That is, as soon as you open the switch, what will happen? No more energy is flowing from the supply to this network, and thus in stored energy, 4 joule energy that was stored in the inductor, that will gradually get dissipated in these two resistances, and the current will as a result drop and become 0. Here we have been asked to find out what is the rate of change of current right after the switch is opened. So exactly like a capacitor voltage cannot change instantly, an inductor current cannot change instantly. Capacitor current can change instantly. Capacitor can uh, withstand sharply changing currents, but it cannot withstand sharply changing voltage, or does not allow sharp change of voltage. Similarly, inductor can withstand sharp change of voltage, but it cannot withstand or will not allow sharp change in current. So we can assume that t equal or t tends to 0 plus, t tends to 0 plus, the current remains constant at 2 ampere. There was 2 ampere current flowing to the inductor. So the question, limit t tends to 0 plus di dt is 2 times our resistance is 4 by inductor is 2, that is 4. There is something wrong. This cannot be positive. Yeah. Can you find out what is wrong? I could. See, look at the inductor that I have drawn here. This thing I told you many times, do not make this mistake, and I made the mistake. I have drawn the current flowing from top to bottom, but the voltage I drew here is wrong. The voltage, if I have to write V equals L di dt, then I have to draw the voltage like this. There I made a mistake, so it becomes minus. It becomes minus. So minus. Now, how did I know that it cannot be correct? Because as I told you, that the inductor current will flow through the resistance and energy will dissipate, so the current will reduce. So the rate of change of current DRT cannot be positive, it has to be negative. Could you understand where I made the mistake? If I have to write V equals L di dt, then with respect to the current, I have to write the voltage like this way only. Okay. I'd be very happy if you find out these mistakes before I do and tell me that I am making a mistake. Okay, then we're almost done for today. Not almost done, we are done for today. So we'll call it a day. Maybe next day we will at same time, Monday 6 p.m. we'll meet and discuss other things. We will see what are there for the next week. Thanks for joining. We'll see you on the next week.